So let's do some examples of uniform acceleration. So one of the things that we discover is if you drop an object and it falls, it doesn't really matter. It always falls with the same acceleration. This is something that was discovered actually by Galileo Galilei, was that you drop different objects of different masses, they always accelerate downwards at exactly the same rate. And so they all have the same acceleration, meaning they all hit the ground at the same speed, ignoring air resistance. So you drop two things going to have same air resistance, they're going to hit with exactly the same speed. There's something that can be done in a vacuum, and it has been done in a vacuum. You drop a light object and a heavy object, and they all fall with exactly the same acceleration. Well, so that means that we can drop an object, fall, hits the ground, has a constant acceleration downwards, and so we can measure that, and we find that this constant acceleration is always the same, so we can give it a special symbol, g, lowercase g. It's equal to 9.81 meter per second squared. In the British units, that's 32.2 feet per second squared. And so with that, then we ought to be able to figure out motions. And one of the labs we're doing this week, it uses constant acceleration, free fall, just things falling. So let's do an example here. Let's say that we have a person right here and they drop an object, and let's say the object is a distance of 1.5 meters above the ground. Okay, so 1.5 meter high, and so I want to know several things. First of all, how long does it take to hit the ground, and then how fast is it moving? Okay, so x is 1.5 meters. Now we know that our equation x equals x naught plus v naught t plus 1/2 a t squared. Now, if you drop it from rest, in other words, it's not moving originally, then v naught is 0. Okay, now, this is where we have to figure out a couple things. What is x naught in this equation right here? And so x naught in this equation depends on how you put the origin. There's two ways of doing this, or more than two ways. Let's say I put the origin up here at the top and I say down is positive. Okay, so if down is positive, that means the acceleration is this way, so that means the acceleration is g. X naught is 0, so this is going to be 1/2 gt squared. So t is going to be square root of 2x over g. Okay, so that'll be the square root of 2 times 1.5 meters divided by 9.81 meter per second squared. Okay, so that would be that comes out to be 0.553 seconds. Okay, so 0.533 seconds. And that's how long it takes to reach the ground. So my next question is, how fast is it moving when it reaches the ground? So starts up here, falls down here. Okay, I just calculated that t is 0.533 seconds. I know that the derivative of our equation v equals v naught plus at. Now, if my origin is up here and down is positive, then acceleration is g and v naught is 0, so this is just g times t. So that's 9.81 meter per second squared times 0.533 seconds. So v turns out to be 5.23 meters per second. Okay. Now I said it doesn't really matter how you set the origin. Let's take the same problem Okay, so same problem. Okay, guy here's dropping an object. X is 1.5 meters here. Okay, that's the distance. Okay, but now let's put the origin at the ground. So how does that change things? So x equals x naught plus v naught t plus 1/2 at squared. So if my origin is down here, if up is positive, the acceleration is down. So that means the acceleration is now going to be negative g. So the acceleration is negative g because I say up is positive, but the acceleration is down. The other thing that changes here is x naught is not 0. X naught is now 1.5 meters. X is 0. So this is going to be x naught, v naught still 0 minus 1/2 gt squared. Okay, and so we do algebra here. 1/2 gt squared equals x naught. T equals square root 2x naught over g. So that's going to be square root of 2 times 1.5 meters divided by 9.81 meter per second squared. And, well, gosh, 0.533 seconds. The same as before. Well, of course it's the same as before. It's the same problem. There's nothing different about the problem. All we did was change where the origin was, and we got the same answer. Okay, what about the velocity when it reaches the bottom? Okay, so v equals v naught plus at. Now, if I put my origin at the top and say down's positive, then a is g. But if my origin's at the bottom and I say up is positive, the acceleration is still down. Okay, so that means the acceleration is negative g. So v naught 0, so there'll be minus gt. And so what does that mean? Well, it means the velocity is going to be minus 9.81 meter per second squared times 0.533 seconds. And so what does that give us for velocity? Well, here's the interesting thing. It gives us the same number as before, 5.23 meters per second, but it makes it negative. Okay, now signs matter. They tell you direction. Last time, the velocity was positive. Now the velocity is negative. Well, what's the difference here? Well, last time we said up was positive. Sorry. This time we said up is positive, so therefore negative means moving down. Last time we had the origin at the top and we said down was positive. And so positive velocity meant going down. So it's really the same thing. They're both saying the velocity goes down. Well, now let's do another example. Okay, same object. We drop it, it goes 1.5 meters. So the height here is 1.5 meters. Okay, but now I'm going to put my origin right here at a height of 1 meter above the ground. I'm going to say up is positive. Okay, we know the acceleration is down. So what does this do to my equation? Well, x equals x naught plus v naught t plus 1/2 at squared. V naught still 0. Now my final position, my final distance is minus 1 meter. My initial position is 0.5 meters. This is minus 1/2 gt squared. Okay, so I do algebra. Okay, so I move this to the other side of the equation, move this over here. So I have 1/2 gt squared equals 0.5 meters plus 1 meter. So in other words, t is going to be the square root of 2 times 1.5 meters divided by 9.81 meter per second squared. And you get the same answer. So in none of these cases did it make any difference where you put the origin or what direction you made positive. You get the same answer every time. And that's the beauty of this, is you always get the same answers. And so you can put the origin anywhere you want. Say the direction's positive. Once you do that, that defines the rest of the problem. But you should say where is your origin and which direction is which. Whenever you're solving a problem, state where the origin is, state what direction it is. That way, when you get an answer, it's obvious from the sign what direction's moving relative to the way that you said.